Okay, so my name is Nicholas Crouch. I work in the National Learning Centre. This is the revision seminar for Applications of Quantitative Methods in Finance, or as we all know it, AQMF. There's a few things that have been asked to do. Anyone who pops up online, feel free to pop in a question. Quite often it helps to put it in the chat, but you can also sort of wake me up as you go along, go, hey, what are we doing here? I'm going to rely on the audience to remind me if I failed to put the thing on the screen. All right, so which looks like we have momentarily. Why is that? Oh, I know what I've done. There's a reason I say these, so that it's like my mental checklist. Okay, so application of quantitative methods in finance. Everything is an annuity, people. Whether you like it or not, it's an annuity. Maybe an annuity with only one payment, but it's an annuity. With some of the stuff you do here, it's actually trying to get you ready for some of the more complicated models that you will see in finance. If you're doing the maths version of financial maths and doing all right, then you're going to find finance easy. All right, there are some tricky things, but that's a lot about trying to understand the terminology used. Right. More, sure. I feel like some chemists have been here before. Okay, so what now? I'm going to just click to. I'm going to be very boring, and you're going to see my page in front of me, because that is the best way to do this. I may refer to lecture notes or something, which I can get in the thing. What is that? No. Okay. Did you have anything you wanted me to go through? Generalized Bayes formula. Ooh. So did you have an example of something you wanted to talk about? That's actually, so one of the things people don't realize is that this financial math actually relies a fair bit on statistics. And so it's actually good to talk about what statistics things. And there's I don't do finance a lot, if that makes sense. So maybe not that, but that sort of understanding how we're going to talk about things. So this is where this would be the thing you're talking about. Let's just pop that there for a second so I can copy it out. So kind of so I've grabbed a textbook. That, and hopefully that's going to work. I need to grab myself a new pen. So, so just make sure we're doing this. If a probability experiment has n possible outcomes in the first stage given by E1 up to 2, and if F1 is an event in the second stage, then the probability that event E1 occurs in the first stage given that F2 has occurred. So this is this horrible thing, that the formula they've gotten. So we've saying, so we've got multiple. So they've only talked about one event in the second stage because we're only going to talk about the probability of this. All right. So there could be also, so for your portfolio, right, you could have an event happen. All right. So you could be talking about the various different share prices rising and falling, whatever. So events that influence that part. What we want to do is we want to talk about that secondary effect. And so what we've got to do, so we want to go, hey, has my portfolio actually risen? And so what we're going to, Bayes' formula is effectively saying, we're going to look and go, how did it affect this first thing? How did that affect whether we rise or fall? And so it's a way of sort of accumulating the change of what's going on. All right. So just, I'm not sure this is possibly going to be slightly different from the way you've actually seen it written, but I'm just going to copy it directly from the book. So we've got this wonderful formula. It's great. Probability E1 is occurred given F1. And so we're going to do a thing. And so the top line, probability E1, I've been a bit inconsistent with my things. E1 times by the probability of F1 given E1. So what we're doing is this is the thing we want to know. So the probability of E1 given that we know F1, but so these things actually quite often associated with drug trials, drug efficacy. So like the probability I have a disease given that I test positive, because the biggest case of this was back when the AIDS epidemic started in the 80s and 90s, was that the tests weren't as good as they are now. And so you could test positive, but the probability that you had the disease, even if you tested positive, was still quite small. I think it worked out to when I was talking to someone who was involved in, he was a mathematician who had been working on some of that stuff. He'd said it's about a third. So you only have a 1/3 chance that you actually have the disease if you test positive, just because of the things. So that's where this thing comes in. But so they have this beautiful diagram. I'm going to do this beautiful diagram in red. And because what's actually happening is we're sort of going, okay, we have these stage ones. So we have like an E1, an E2, and so on. And there's a lot of them. So the last one we're going to say is E1. And at every one of these points here, I've got several different outcomes. All right, and this would be F1. We're just going to label that first one. And if you look at what this is doing, so if we go back to the basic probability rules, this thing here is actually giving you, so probability of E1 times by the probability of F1 given E1. This is actually equal to the probability of E1 intersection F1. And so all these little bits here are the cumulative parts of F1 intersection with one of those E's. All right. Now, one of the things this expression hasn't said is, so I would have used that. So rather than this complicated way of expressing what the E1s are, I would have said the E's represent a partition. So you've heard the phrase partition. So we can actually do this when we sort of, sometimes they may not have intended this to be a proper partition in that it didn't cover the whole set, but this formula implies that they're disjoint. But the thing that's important is that we can actually complete it as a partition. Like if I have a series of events that doesn't cover every possibility, I can add in the last event, which is none of the previous events. And to make it a partition. And so that's why we can apply this formula. I think this particular textbook is aimed at sort of economic and finance students, and that's why they've actually gone this way. So I wonder if we've got a nice example for us to talk about. Blah, that's going to suck. So we can. Oh, they've got a horrible thing. That's wonderful. So what have they actually done as this? So if we talk about this, they've gone, suppose a test for diagnosing a certain serious disease is successful in detecting the disease 95% of times of all persons infected, but it incorrectly diagnoses 4% of the time in all healthy people. And there's 1%, there's 4%. Suppose also that it incorrectly diagnosed 12% of all people having a minor disease as having serious disease. This is known as it is known that 2% of the population. So what we're going to do is, if we're going to put this in, we've got that. So we're going to go, the thing we're going to do is we're going to get the test result, but that's like your F1 for this particular example, isn't it? All right. I like this one because it's got like 3 possibilities. So we're going to divide into disease. They have a mild disease and they have a healthy. And so it is known that all people having minor disease have minor disease as having serious. It is known that 2% of the population have serious disease. 0.02. 90% of the population is healthy. 90. And so that means an 8%. Good. 0.08. Yep. That's the other problem with this. Let me switch this over. Yeah, that's there. Sweet. And now, so actually got 2 outcomes from each one of these things. I've got a positive test and a negative test. So positive, negative, positive, negative. All right. So we said the test. So diagnosing serious illness, successful detecting disease in 95% of persons infected. All right, so if I have the disease, the probability of a positive test is 0.95, and so therefore the probability of a negative test is 0.05. Diagnosed 4% of the healthy people as having the disease, so if I'm healthy, 0.04 and 0.96. Sweet. Suppose it incorrectly diagnoses 12% of the people with minor disease. So this is, we're going to call that 12, and we're going to go 0.88. Sweet. All right. So first thing we could go, so we actually, when we talk about doing this, we could go probability of positive. All right. Going to go through this because that's actually, if we look at this formula, that's actually effectively what this is. All right. So this is going to go, it's going to be equal to probability of having the disease times by probability of testing positive given we have the disease, plus probability of mild disease times by probability of testing positive given I have mild disease, plus probability of healthy times by probability I test positive given that I'm healthy. All right, horrible thing. And so I want it to be there. And so I can just copy the numbers in at this point in time. Probability I have the disease is 0.02 times by 0.95 plus 0.08 times by 0.12 plus 0. Sorry, try that again. 0.90 times by 0.04. All right, which is equal to, and at this point in time, I wonder if it's going to swap over. No, what I'm going to do, oh no, cool. So you will notice that through the week, what I've been doing is I've just had an Excel spreadsheet open when I want to do calculations. I actually expect you guys will actually appreciate the doing Excel spreadsheet to do these calculations, because you should have done it before. So the probability I test positive, 0.0646. Sweet. I'm going to actually just open this up a little bit. No, no more decimal places. Okay, so now we want to know probability of disease. So we actually want to find probability of disease given a positive test. So, oh, yes. That is what I wanted to do, but it didn't happen last time. And so, maybe I didn't share the Excel screen with the Zoom. Maybe it's shared it on there, but not on the screen. Okay, so when we do this one, we actually want, so we want to go probability, I put probability I test positive and have the disease. So the probability of disease times by probability of test positive given disease on, no stress. Now, this is that probability I had disease times by probability of test positive given disease plus ... probability of healthy times by probability of positive given healthy. All right, all this stuff. We worked out this denominator ahead of time, and so we should do the numerator. We should actually do the numerator. Now I'm going to go in. I don't think that's, no, what we're going to do is I'm going to stop sharing this. And then you start sharing. That should be that. And so all I'm going to do, so this was the bit where I worked out if I look at this one, this was the bit where I worked out what that denominator is going to be. It's useful to do that ahead of time because it's a horrible calculation and we don't want to do it inside our calculation. Now all I'm going to do is go 0.02 times by 0.95 divided by this number. Ooh. And so this is actually telling me just what I was saying before. Disease given positive test is equal to, this number says 0.29, and we're going to say 4. All right, or 29.4%. So, and I'm going to go, all right, let's do that one and that one. All right, so we can actually see that the probability I have the disease, given that I test positive, actually not very big. All right, we could actually do a similar thing. So we could go, what's the probability I have? Let's give that a go. Let's just put that up a little bit. So what's the probability I have a mild disease given that I test positive? So probability of mild disease given test positive. And so it's going to be the same type of thing. Probability of mild disease times by probability of a positive test given mild, all divided by, I'm just going to call that probability of positive test. All right. So we understand for that base law, that denominator is just the probability I test positive. Okay. It's a complicated way of putting it, but that's what it's saying. And so in this case, we're going to have a 0.08 times by 0.12 on 0.0646, which is going to be equal to, we won't bother trying to show you the actual Excel calculation, but we're going to go equal to 0.08 times by 0.12 divided by total probability, 14%, 14.86. 4.86. We would possibly call that for 14, I'm going to say 9% round up. All right. So if you think about it in the media, quite often, if you're watching the news, you wouldn't see them say 14.86, whatever. They'll go to 14.9 or possibly just 15. All right. So some point in time, rounding, doing the appropriate rounding is the right thing to do. So you can actually see that this test, sort of more than 50% of the time is going to be a false positive. All right. I'm doing a trick where I go, if I had that number and that number, I get just slightly less than 45%. And so the other 55 must be a false positive. All right. I know it's kind of weird, but this is one of those things that happens with tests, is that a positive test isn't necessarily as damning as people think. All right. And that was actually one of the problems with the initial COVID tests too, that there was a fairly high false positive rate. And so that's why we kind of possibly re-entered the lockdown way more than we needed to. Okay, so does that explain what's going on there? All right. There is with some of these probability rules, right? The thing I was saying, where did I write it down? This thing here, this idea here, where this thing is a fancy way of saying the probability of E1 intersection F1. The reason that I've sort of then gone, hang on, this thing here is a fancy way of saying the probability of F1 is that it's counting for the intersection with E1, the intersection with E2, and so on and so forth. And so it's the total probability. I'm assuming that the event E1 up to En form a partition. All right. And like I say, it is implied by this particular expression that they're mutually exclusive. Doesn't imply that they cover the whole set, but I'm going to, like I said, you can sort of just add in the bit that it's not covered to make a partition. So that's one of those things where we want to understand that there's that paradox a positive test with some of these, with recent, doesn't always mean that there's a high likelihood of actually having the disease. It's a bit of a test, actually. So, all right. Was there anything else you wanted to talk about? Because most of what people were asking me to do um, so this was an income stream where we have a thing. This is sort of effectively going an income stream that looks like e to the minus rt. So, do you recognize this type of function? Yeah. Oh, okay. And that's a specific, that's not like a surge function type of thing. So this would be maybe or possibly a movie. So you have that massive peak, but then like you still find people buying copies of say 30 years down. So there's some movies, some like Disney movies, people still buy, and so it has a tiny trickle slowly. There was two variable calculus stuff, including contour diagrams and differentiation by parts. I think this is sort of like this might actually really mean chain rule. For multiple derivatives. So there would seem to be a lot of concern about the partial derivatives type of thing. So you're okay with that? This is where you guys are here. If you have something we want me to talk about, please just sort of jump in. But otherwise, what I'm going to do, because making stuff up as I go along is actually a lot more challenging than it looks. I might actually refer to, so for those people playing at home, we have a beautiful textbook. This one, oh, there we go. Try and get the light off the sheen off. This one is the one that was recommended for this course some years back. And so I'm going to look through this one to find something about partial derivatives and contour curves, because all we want to do is find something that sort of, we don't want to make it too hard. I often do this. Oh, okay. That's fine. All right. So there are funky things. Oh, did you guys use MATLAB? Because you can actually, you can actually make MATLAB draw some of these multivariable functions. And it's kind of cool. I won't try and do that now because that's a terrible plan. Oh, actually, yeah, that would make it a lot easier because with MATLAB is great. Don't get me wrong. But also it has issues, right? There are things. There are some things. I don't. If I thought about this, I would have grabbed my little models because I was going, oh, we could have a Cobb-Douglas equation. So what we're going to do. So with some of your Cobb-Douglas functions, Q is equal to, this one's got 4, K to the 0.4, L to the 0.6. So there's two ways that can happen. This is just saying that my capital and my labor have different powers, but that total power works out to be 1. So there's variations on cob logos where that doesn't, where they don't always come out to 1. But one of the things about functions like this, all right. So if we just, I'm just going to do a bit of a, if I do the partial of Q with respect to K, all right. So my 4 is a constant. My L to the power 0.6 is a constant. That's one of the biggest, that's like the biggest lesson for doing this there is. And then I'm going to have my K, but I'm going to take away 1 from my power. So 0.4, take 1, and I'm going to times by the power, 0.4. So times by the power, take 1 from the power. This I'm going to write as, so I'm going to have 4 times 0.4, L to the 0.6. Because this is going to work out K to the minus 0.6, so K minus 0.6. I'm actually going to write it out as, I'm going to simplify this down to 1.6, L to the 0.6, and K to the 0.6. Because it's got a negative power, I can put it in the denominator, and I can write it out in that way. Okay, so this sort of thing, because these sum to 1, there's actually a property. If these powers sum to 1, I'm always able to write it. So if I do the other partial of Q with respect to L, same thing, 4 times K to the 0.4, because we're holding K constant, it's partial with respect to L. And so then we're going to times by the power, 0.6, L to the 0.6, take 1. Now I'm going to put those together and go 2.4, K to the 0.4, L to the minus 0.4, and so I'm going to write it out in the same way. 2.4, K, 0.4 on L to 0.4. Okay? So nice and simple, and this is a nice form. Okay, so one of the other things that happens with this, right? So these things have this weird property where if I was to talk about the contour curves, right? So if I was to fix a value for this thing here, so when I do contour curves, I fix a number, I fix a level of output, for example, and then I work out what values that gives me. All right. So if I was to say, I'm going to do this in red, let Q equal 4, right? Then that's going to be equal to 4, K 0.4, L 0.6. Wonderful stuff. This is going to allow me to go 1 is equal to K to the 0.4, L to 0.6. Or I'm going to write it as 1 on L to the 0.4 is equal to K to 0.4. 6, that needs to be a 6. Wait, these things you're right. We should, yes, there's must be right. Sweet. And so I can actually just go, I'm going to go 4 times y to the power 0.4 times by x to the power, power 0.6. And so I'm going to try and change this to that so it doesn't try and treat them as sliders. It's going to give me a line, isn't it? Oops. No. We're going to not do that. Oh, I need to do that to make it happen. That's what I'm expecting to see. Good. All right. So we're actually going to get this sort of thing happening. And so if I was to change, I was to make that 0. If I make Z negative, goes the other way. I make Z positive, goes the other way. And so it's actually really hard to sort of visualize. I wonder if I can do. I wonder if I can go. No, I don't think that. All right, play with this enough. Can I make it a 3D plot? No. All right, I'm going to worry about that another day. All right. So just to sort of try and replicate, I'm only going to concentrate on what was happening in that first quadrant. Okay, so I'm going to concentrate on what's happening in the first quadrant. And so we saw when the value was quite small, we had a line like that. But so this was sort of Q equal to 1. When I increased the value, it is to say 4. And when we went out a little bit further, and so this was Q is equal to about 10. We can actually see this thing coming together to create contour curves. What we're actually going to do when we calculate contour curves is literally, we're just putting in a value. This is not a great example for doing contour curves. It is a great example. This thing, I love this thing, where where it works out. And you guys have to do some economics. Yeah. So these are things that crop up in economics. That's a microeconomic thing generally. And it can be useful to sort of know that this particular feature of the derivative. Okay, so let's try and find something a little bit more fun to play with in terms of multivariable functions. There are some things that we just know are going to work out nicely, right? So there are some things, like one of the things was going, one of the standard ones is if I do sort of Z is equal to X squared plus Y squared. All right. And so this thing here, what we're supposed to do is recognize that that's the equation of a circle. All right. And so this is like the square root of the radius. All right. And so what's going to happen if I try and just sketch this very roughly? So my Z, this bit's always positive, so my Z value doesn't go negative. And so what we're going to get is at any height, we're going to get like a circle as my contour curve. All right. And so at the bottom, it's going to come through here, and it's actually going to have this nice parabolic arc around it. It would if I drew it nicely. All right. And so I'm going to have these nice. Now, how do I know that's what's going to happen? Yeah, that's what you're thinking? So all I'm doing here is I'm going, okay, let's make, if I make Z is equal to 1, so Z equal to 1, then I have 1 is equal to X squared plus Y squared. This is circle. of radius 1. So when z is equal to 1, I've got a circle of radius is equal to 1. All right. So if I make my z equal to 4, so I have 4 is equal to x squared plus y squared, then then this is going to be circle of radius 2, so square root of this value. And so I can see that these things are going to come out nicely. So if I look down on this, if I did my contour plots, this is actually just going to be a series of circles. Drawing circles freehand is not a lot of fun. What's going to happen if I go up in equal increments, these circles are going to get closer together. That much money to borrow by hand. And so I can see these coming from below, okay? Interestingly enough, so that's actually sort of cutting slices. So a contour curve is like a projection down onto the plane. So we're actually trying to draw a two-dimensional representation of this thing here. And so we have to know how those things look, all right? So we could have a little thing where maybe those were sort of wavelets coming out. So another thing to do might be to look, if I just cut this, if I did a cross section of this, cutting down this way, I would actually get a parabola. The way I've written this one, I would get a parabola. All right. And so if I was to move that forward, if I was to slice that but forward by 1, what you're going to get is you're going to get a parabola that comes through here. All right. And so I can actually sort of, this is like slicing horizontally. This is like doing a vertical slice. Okay. And I can sort of, that's going to allow me to build up a complete picture of it. I'm kind of going a little bit off script. A little bit, because I know you guys don't go that far. They want you to just focus on being able to do these level curves. And all you're doing in that situation is doing horizontal slices. You're fixing a value of z, all right? But if I was to fix a value of y, say, then I'm going to see this equation, that equation becomes a parabola, the equation of a parabola. Okay, and that can help you understand what's going to happen. So sometimes if you're trying to visualize the curve for yourself rather than necessarily answer questions, that same process, so this gives me an idea of what's going to happen, but I can actually do the same process for a different variable and think about it as slicing this way. So could be doing a vertical slice down this way or a horizontal slice, or even sort of, fix a value of x. And it can give me an idea of what that picture looks like. This thing has a special name. Mathematically, this is, what is it? No, it's parabolic, that's right, parabolic. So parabolic ellipsoid. All right, because one direction, it's a parabola, the other direction, circle, ellipse. Okay, so now you kind of saw me just go, it's going to be this, didn't you? All right, there's a whole range of functions that we kind of expect you to recognize. So there's a little bit of going, this thing, so this thing I'm going, ooh, that's going to be a circle type of thing. If I'd had a 2 or if I had some coefficients on these things, but they're both still positive, I would be going, hey, that's still an ellipse of some description. All right. And the same process is still right. And still work out. If I want to work out where it's going to intersect an axis, I would just put in, x is equal to 0 to get my y-intercepts, y is equal to 0 to get my x-intercepts. And those can help you find some points on your curve. I can know roughly it's going to curve. I can find myself a set of points. I can draw my curve neatly through that process. That can be a really nice way to do these things. I don't want to do that. None of these are fun. Oh, that could be fun. Sure. let's try this again. So that's if I know something about this curve. All right. Let's see what happens if we do z is equal to, this will be interesting. So there's one of the other secrets about exams. All right. That thing is not going to be easy to deal with, right? I would have to actually throw that into GeoGebra. Let's go back here. Let's do this. All right. So we saw it didn't like doing things. So what I'm going to try and do is I'm going to do 4x squared plus x squared minus 6y 3 minus 7 is equal to, we do 0. Wow, check that. Okay, so weird looking thing. All right, let's just try this. Actually, you know what I might do? Right, no, let's go back and change that number. All right, so we can actually go through and put in, let's go to the omega, change minus 10. Okay, ooh, that's interesting. Okay, so we can see strange sort of behavior happening. All right. When we're doing this, this is way too complicated for you to actually do by, like, you couldn't draw level curves. Couldn't. I got carried away and you couldn't actually do level curves of that. All right. So just to put this on the paper, so this thing had, so it's going to actually notice how it had that sort of parabolic shape. If I'd made this equal to -7, all right, so we were just looking at that part, it would go through 0, 0. But when we didn't, so if I made the number more negative, I got sort of parabola that fitted inside there. If I made this, made Z more positive, I actually brought it out, but it very quickly tended towards that outer line. Haven't quite got that sorted out properly. How could I simplify this so that I could do it? No, I can't do that. So we're going to move on to doing, what could I do about partial derivatives? This, yeah, that's like, what? No, you're never going to get that, right? You're going to get very boring things like this, or even worse, you're going to get things like the things that where you're going to be asked to draw contour curves are going to be very simple. All right, because I love the idea. So sometimes, so back, you know, as you may have guessed, I've done a lot of maths in my life. And back when I started doing it, when we were asked to sketch things, we're actually told to do the derivatives. So I'm going to do partial derivative of z with respect to x. So doing my partial derivatives, same process all the time. All right. So because this is partial derivative with respect to x, we're holding y constant. And so those two terms are actually constant with respect to x. And so I'm not even going to consider differentiating. I'm just going to go hx plus 10x. This is like the 5. The y squared there is like the 5 when I do this. All right. Now, so z with respect to y, same approach. So this is going to be 10x squared y plus 18 y squared. Okay. What on earth? So I don't know. The textbook's kind of implying to me that this thing has a critical point. All right. This is probably a bit too complicated for an exam question, but you could be asked to find the critical points of this function. All right. I have this feeling that somewhere around here there might be a critical point. So one of the first things to go, that's where the partial derivative of z with respect to x is equal to 0. Nice work. Thanks. I'm supposed to be somewhere. I'm not going to make it. So if I was to do this first one, 8x plus 10xy squared equal to 0, I can actually factorize this. I'm going to put a 2x out the front, and this is going to be a 4 plus 5y squared is equal to 0. Okay. That thing is going to tell me that x is equal to 0. That implies x is equal to 0, or 4 plus 5y squared is equal to 0. I am going to go, not possible. Not possible. All right, why do I know it's not possible? The reason I know this is not possible is y squared is always a positive number, and I've got a 4 and a 5. So 4 plus positive number times positive number is never going to be able to be equal to 0. All right, best I can do is make this equal to 4. And it's either 4 or up. So to get my first order partial, my x partial derivative equal to 0, I actually going to have x is equal to 0. And so I'm going to do the same thing. Because this has given me an exact value, all right? So because this has given me an exact value, all right, I can then go, so my partial of z with respect to y, x equals 0, all right? I actually put in, the only way I can have my first order derivative equal to 0 is have x is equal to 0. I can now put that into my y, and if I put that into y, that will be like 10, 0 squared times y plus 18y squared is equal to 0. This is just 18y squared is equal to 0. And so therefore, y is equal to 0. Knew it. Knew it. So we have one critical point at 0, 0. Anyone want to guess what type of critical point it is? No. I'm going to say, I reckon this is a saddle point. How do I work out if have you done the classification of critical points? So you know about the Hessian. You still call it the Hessian? Fancy matrix of second order partial derivatives. So I'm going to create this matrix, which is like f, x, x, f, y, y, f, x, y, f, y, x, f, y, y. Yes? No? Oh, okay. So I've written this as a matrix, and these straight bars along the line mean that I'm doing the derivative. So this is f, x, x times f, y, y minus f of, well, it's like x, y. Strictly speaking, it's like that. But your theory also says that these two numbers are the same number. All right? Yep. Yes. So f, x, x, f, y, y minus f, x, y squared. Same thing. Because these two are equal, I can say they're the same thing. Let's do some partial derivatives. So what I'm going to do, I've already worked out my first order partials. So if I do so this will be second order partial of z with respect to x twice. So differentiate that with respect to x. I'm going to get 8 plus 10y squared. So if I do the derivative of z twice, but with respect to x, And now with respect to y, so I differentiate this with respect to y, I'm going to get 20xy. Slick. Quietly, if I check this, if I do this one with respect to x, that's going to go to 0, differentiate that, I'm going to get the same thing. Woo, it does check. Quite often I will check because I am really good at making mistakes. All right. You would think after a lifetime of doing this stuff, I wouldn't be, but you'd be wrong. That's going to be 36y. Oops. Oh yeah, no, good, good. Now, if I evaluate all of these things, so sort of z, x, x, x at 0, 0 is going to be equal to h. My z, x, y evaluated at 0, 0 going to be equal to 0. And my z, y, y evaluated at 0, 0 is going to be 0. Do you know what this means? I have 8 times 0 minus 0 times 0 squared, which is equal to 0. Yes. All right, good. This can happen. All right. It's unlikely that I'd do that to you. If I was writing the exam, right? It's unlikely that I would do that to you in the exam. All right. I will try and make it like, because we know if this value is negative, we call it a saddle point. So there's a, what do you call this? Do you give it a H? Do you actually call this value a specific, give it a particular thing? I didn't look enough at the notes to work out. Oh, delta. That would be delta. So delta less than 0, you get a saddle point. Delta greater than 0, max, whoops, or min. All right. And so then x, y, y. We look at either of these two to determine whether it's a maximum or minimum. All right. But if it's equal to 0, we have this horrible undecided thing. This thing, oh, you know what it is. Oh. If I was to sort of work along this axis, this thing, if I was to work along what would be the y-axis, all right, so I've got my z coming up here, then what's actually happening is, I reckon that's coming that way, and that's going to do that. So I reckon, without being 100% certain, that this thing is going to do that sort of thing along the y-axis at 0, 0. And so this is why it doesn't qualify as a local maximum, local minimum, whatever, because it's actually, from the y point of view, it's going to actually be a point of inflection. You've talked about points of inflection. Good, I can do that. Beautiful. That's actually, so from the point of view of demonstrating what's going to happen in the exam, possibly not great. One of the things I really want to sort of pause here and sort of go, sometimes, like I did this myself writing exams when I first started. I made mistakes in the way I'd written the question, dropped the minus sign. and I changed my thing from being nice, sort of, there's going to be a local maxima here, to, oh, there's actually something really weird going on. All right. And so the question that I intended to ask wasn't terribly difficult to answer. The question that was in the exam was more difficult to answer. All right. And a lot of people got thrown by that. One of the things to remember is to remain calm. All right. You're going to do a couple of things. You're going to actually make sure you put in all the work. And see if you've done all of this and you go and you can't see this sort of stuff happening, right? Because I wouldn't expect you guys to be able to visualize it in that way. Then you've just got to go, well, the number says it says it's undecided. And that's all you can do. Okay. But if you put down all the working that you can do, and it goes, and someone like, there's been a mistake, and, everybody does it. The head of the School of Maths, not the current head, but one of the previous ones, wrote a question in the exam that is a known unsolvable problem, simply because they miswrote what they intended to put in, all right? They intended to put in a problem a little bit complicated, a few tricky steps, not impossible. Ended up putting in something that was impossible, all right? The students who did well with that question were the ones who wrote down, did the things as they were expected to do, and then gone, oh, I can't do that. And just sort of gone, hey, I can't do this. I'm going to let it go at this point in time. Okay. Because you've demonstrated the techniques you've been given, and then something's gone wrong. All right. If that sort of stuff happens, we take that into account. That's one of the other things to really bear in mind. That is taken into account when something like that happens. And it's, we're human. We make mistakes. There is now a lot more procedures in place to avoid that happening, but it's still possible that something gets through. All right. Or it might have been that it was noted that that sign needed to change, and it just never happened before it got printed. Too bad. So if we write down all the steps, if you make a mistake, we see what you were trying to do. We can give you marks for what you were trying to do. If we make a mistake, we can see that you actually took the appropriate steps, and it didn't make sense when we got there. And just clearly something's gone wrong. Let's go. All right. Okay, we've talked a little bit about that. Oh, and we got something that's not terrible. We should do that. We should just do that. No, that's a terrible idea. If you were to ask to do partial derivatives by first principles, so we're going to go 5. Partial derivative. Okay, let's think about a not difficult function. I'm going to go x squared y plus, let's just do x. Okay, making it slightly difficult, but not. All right. Find partial of f with respect to x by first principles. Okay, so this is going to be, so partial of f with respect to x is going to be equal to limit h goes to 0. F of, because it's with respect to x, we're going to go x plus h, and then y minus f of x, y. All right. Nice and easy. So we write out the formula, and then we write out what that means. All right. So this is going to be x plus h squared times y plus x plus h minus, I'm going to put brackets around this, x squared y plus x all on h. Okie dokie dokie. So So going to be honest, if you see a question like this in the exam, you should be going, woohoo, this is just follow the process. I don't necessarily see what's going to happen yet, but I can be fairly confident I'm going to get this right. I'm going to expand this out, go x squared plus 2x times h plus h squared times by y plus x plus h minus x squared y minus x. Don't be afraid to do lots of writing. The actual writing process isn't that bad. 2x hy plus h squared y plus x plus h minus x squared y minus x, all on h. All right, at this point in time, I'm going to start cancelling things. So I've got an x squared y and an x squared y, they cancel. I've got an x and I've got an x, they cancel. Everything else I'm left with, let's just quickly, we've got that term, that term, that term. That feels like a thing. They've all got h in them. So what I'm actually going to do, limit h goes to 0. There's a h through all of those terms. So if I take it out of that, 2xy plus hy plus 1 on h. At this point in time, I can cancel out the h. So notice how I've made sure I've taken h out of every term in the numerator before I've then cancelled it. All right, I want this to be h times everything in the numerator before I cancel it. Now, I can actually do the limit as I can actually take h to goes to 0. And if h goes to 0, that term goes to 0. And so this is going to leave me with 2xy plus 1. And because it's a partial derivative, I can just go, that's actually what I would expect to be the correct answer. All right. This is about as complicated as I expect to see this, or not as complicated. All right. And so part of me looked at the option, some of the functions on the page, and go, oh, we could do that. And I'm like, oh no, that's a limit you guys don't know how to do. So can't do that. So with it, like I say, if you write down, right? So the other part about this is if you just get to that bit there, and maybe say you've made a mistake, and things aren't cancelling the way you expect them to be, then this is still half the marks for the question. All right. I've said this, basically everyone marked a lot of exams in my life. All right. And it's not actually true, but for the people who don't pass, one of the defining characteristics is they didn't answer a lot of questions. They wrote nothing. All right. Now, I would be prepared to bet if I was to sit next to them and said, what's the first thing you should write for that question? Almost all of those people would be able to write the first thing that you should do. All right. And if you know the first thing to do, then you write the first thing to do. If you only know the first thing to do, you write the first thing. All right. So if you know that it should look like this and you can't work out what you've done wrong, you say, I expected it to look like this, but I can't see what I've done wrong. If you get to here and you go, I can't see it, I've missed this term, it shouldn't have a factor of h. You go, hey, I made a mistake somewhere, that term should have a factor of h, so I can cancel the h. You say that, and then go, let's pretend it is 0. Take it out. You tell them what you expect to see, because that's telling them what you know. All right, the exam is getting you to demonstrate what you know. Okay, so we did some first principle stuff. Geometric interpretation of curves is really hard, but I've sort of talked about that, doing those things. We are going to do, I think what I might do is I might try and do some upper and lower sum stuff. And then we'll go on to doing some of the integration stuff. All right. So upper and lower sums, because I'm running out of time. And so no. Okay, so quickly going to recap some of the sums. Right. So sum of 1 from I is equal to 1 to n is just equal to n. Sum I is equal to 1 to n of I is equal to n plus 1 on 2. I'm not sure that you're actually expected to know this one. Wrong number. N I squared. This is n plus 1, 2n plus 1 on 6. I think the other one you are expected to know is sum of x to the I is equal to 0 to n, should be 1 minus x to the n plus 1 on 1 minus rx. And if absolute value of x less than 1, sum I is equal to 1 to infinity of x to the I is equal to 1 on 1 minus x. All right. These are associated with geometric series. You should know about geometric series because that is actually a thing that happens for oh, okay. Okay, sure. So let's, I don't know, do we have a fancy thing? Yeah, I'm just trying to think, having a bit of a pausing momentarily to see if I can think of something that's fun, but not too difficult. And the answer is no. So we'll either do something fairly boring. What we'll do, we'll do this. We'll go, we'll take y is equal to, I'm just going to go x squared. All right. So we're going to do, this will be, we're going to do integral from, say, 2 to 4 of x squared with respect to x. Yeah. So we've got these summation things. Like I say, this is the only one I don't know that you need to know. I know you should be expected to know these. I know you should be expected to know these. This one, but since I've written it down, if I'm going to do, so back in the day when I tried to write exams for this sort of this course, if I was going to ask something that involved knowing that sum, I would include it in the information of the question. Okay, so you may get them, they may do that to you. Upper and lower sums is very standard. A is equal to 2, B is equal to 4, your interval width. So remember, we're setting up a partitions. And so we're going to break our interval 2 to 4 into n steps. All right, so I'm going to go, this is always going to be B minus A on n, which is going to be 4 minus 2 on n, 2 on n. And so xi is always equal to a plus I times delta x, which is equal to 2 plus 2i on n. Xi squared is going to be equal to 2 plus 2i on n whole squared. All right. So I'm actually going to work this out ahead of time, right? So I'm going to go 4 plus hi on n plus 4i on n squared. 4i squared on n squared. All right. So by observing that the function is increasing on that interval, I can say my maximums I are f of xi, which we have just worked out to be 4 plus 8i on n plus 4i squared on n squared. So my upper sum with n intervals is equal to. So quite often we do this. First thing we do is put the delta x, the interval width, outside the sum, because it's going to make your life easier. This is going to be I is equal to 1 from 1 to n of your maximums. We interpret what that is. All right, so none of this so far has been difficult, right? This is all just doing the things that we're expected to do. All right, and again, if you get an upper and lower sum, this is just the thing. The hint can be sometimes they'll put a number here, 4, 5, 6, 27, whatever. And so that's when it says we're going to do it some other number. Specifically, they're going to, if we're asking you to do it in the exam, that number will be small. I've seen it as low as 2. I've seen it as large as 6. So quite often, if it's a difficult upper or lower sum, I'm going to make it a small number. If there's something else I'm expecting you to notice. So this is the standard general form of upper and lower sum. And so I'm going to go 2 on n, sum I is equal to 1 to n of this stuff. So 4 plus 8i on n plus 4i squared on n squared. We are going to do this way. We're going to go sum of 4s plus the sum of my 8s I on n plus sum of my 4i squared on n squared. Okay, this one, nice and easy. So when I come down here, 2 on n, this one, 4 n. This one here, I'm going to put my 8 on n out the front and go sum of I is equal to 1 to n. And then I'm going to go plus 4 on n squared. So these values are constant, and I'm bringing them outside the summation. All right. This is, again, all things we know about our summations, all right? But these are also where you start to actually need to understand what's going on and can cause problems in the exam, all right? We understand brain doesn't always turn up like your body in the exam. So we're going to go 2 on n, and this is going to be 4n, and this thing is going to be plus 8 on n times by, we've got a formula. Where did I write the formula? That one. This is going to be like n plus 1 on 2 plus 4 on n squared. And then we've got a different formula, n plus 1, 2n plus 1 on 6. Okie dokie joke. Brilliant. Sure. I love the plan. All right. Start expanding this out. 2 on n times 4n. 2 on n times 8 on n times n plus 1 on 2. Well, hey, I can start doing a little bit of cancelling out of stuff here. Sweet. I like the cancelling of stuff. Plus 2 on n times 4 on n squared, n plus 1, 2n plus 1 on 6. My n's are starting to cancel. This is going to get me an 8. This thing is going to get me 8n on n plus 8 on n. This is going to work out to be, I'm going to cancel that with that one to make that a 3. And so that's going to be plus. And so I'm going to have 2n squared. So 8n squared on n squared on 3n squared plus If I do this, this is 2 plus 3, so that's going to be 3 times 4 is 12n on 3n squared plus 4 on 3n squared. That's going to cancel with that. That's going to cancel with that. That's going to cancel with that. I'm going to get numbers. So I've got an 8 plus an 8. That's that number. This is actually a number plus an 8 on 3. And then I'm going to get 8 on n. And that's going to be, so we're going to write this as 24 plus 12. That's going to be like 36 on 3n. Sure. I could cancel that down. Sure. And plus 4 on 3n squared. Okay. This number, 16, 20, 18, and 2 on 3, plus this can divide by 3, so this is 12 on n. Can't do anything with that. All right, sweet. Upper sum that number. Okay. Yes. Don't look like you followed me there. Do I need to go over something else? Do I need to do this slowly? That's just the upper sum. No. So if I'm doing this in the exam, want to be a little bit careful because I may have gone, if I'm this is it's just a bit of work, right? It didn't, if you look at actually how long it took me to do, it didn't take very long, but it's a bit of work and there's a lot of places where you can make a mistake, all right? Doesn't means that it's not actually a great exam question because it doesn't, it's making you do a lot of calculations where you can make a mistake, but it's only testing 1 or 2 basic concepts, all right? So it's not necessarily the best thing for an exam, but it's still possible. They've definitely done it in the past. Swings and roundabouts. There's actually a trick, all right? Yes. So if I'm doing my lower sum is equal to 2 on n summation. And so this is like f of x I minus 1. I is equal to 1 to n. Yep. I can write that as 2 on n summation I is equal to 0 to n minus 1 of f of xi. This makes it a lot more like the thing I've just done. All right. And so some of these things here will go to n minus 1 and n. So n minus 1, n, 2n minus 1. And so it will be very similar. I'm not going to do this because it's really boring. And I've got better things to do. And you have better things to do right now. But I'm going to go, because this is a quadratic, all right, I can actually say, assuming, and this is assuming I've got the calculations right. I make mistakes all the time. That I can do that working out. I can do this nice shift. This shift will make the calculations involved in that easier. And I can go, it's going to be this. This is what it's going to work out to be. I only know this because it's quadratic. All right. So I've taken a quadratic. So that's one particular thing that we'd be looking for. Okay. And the other thing we might do is we might give you, well, actually it was in year 12 exam from a couple of years back. One of the year 12 mathematics exam from a couple of years back. They gave you this function. And you were asked to do, so, and then they didn't actually get you to do exactly this, but find upper sum on 4 intervals for All right. They did actually tell you what the equation for this function was. What's the trap? Why would they do that? All right. If I was to do this, if I was to have my x 0, 1, 2, 3, 4, all right, f of x. This number is 0. That actually set it up so this was a nice number. I'm going to pretend it's 1. And then we're going to go 0.75, 0.35, 0.25. Something like that. Those are very rough approximations for the thing. What is the maximum value on the first interval? 1. So when I'm doing my upper sum on my 4 intervals, my interval width is 1. And then this is going to be f of 1 plus that second interval, the maximum value is also f of 1. Okay? So that I can actually work out these numbers. So when you have a turning point, creating yourself a little table of values, notice where the turning point is. The previous part of the question in the Year 12 exam showed that the maximum for this thing was at this point. All right. You would be expected to find the maximum value in that region. So, and so then we're just 1 plus 1 plus 0.75 plus 0.35 is equal to 3.1, I think it works out to be. So if there is a small number of intervals, the trick is that there is possibly a turning point in that region, in that interval, and you need to adjust your upper and lower sum to include the true maximum of the function in that region. Okay? That is a bit of a, that is a thing that they will do. All right, so let's pop that there for a second. Okay, so possibly you should also remember to say that all of the stuff I do, this recording, these pages will go up online sometime this afternoon or maybe tomorrow, so that you can look over this if there's something you've missed or something that, yeah, want to check. Or if you're, all the other revision seminars, David's done some of the some of their applications of quantitative methods. I've done others. So David has a different way of presenting stuff than I do. So that can be interesting to see how it's doing. Possibly the last thing, we're actually running out of time. And so the last thing we might do is talk about techniques of integration and how to recognize what you're, so you don't have a lot of techniques of integration. And the answer is going to be, it's to do with the words. Techniques of integration almost always boil down to a substitution, but there are some cases when you will need to use a integration by parts. Really, words not. And so I'm up to page 8. Okay, so let's just, so the one that was mentioned here, if I do like integral from like 0 to 10 of, so this thing here is a type of surge function. All right. So this is actually, roughly speaking, what that graph looks like. All right. Very roughly speaking, this function has a graph that looks like this. Okay. And so it wouldn't be impossible that they're actually going to ask you to actually calculate the actual integral by hand. You guys, Year 12 students? No. You guys? Yes. Okay, so why is it hard? All right, first thing we're going to do is we're going to write this as 5 integral 0, 10 t e to the minus 0.05 t dt. This would recommend, this could talk about the total income from like I say, like a movie that you make. It might be a bit of a slow burn to start off with, but then there's going to be a peak. But as time goes on, the income stream is going to tail off. All right. And so what we've actually got to do, so we've got to understand that with integration by parts, the formula is like FG is equal to FG minus integral FG. It's not exactly that, is it? But the thing is, I've done this so often that I know that if I put the dashed on one of these, then I put it on the other one here. All right. And this is just F times G. Okay. That makes it easy. Now, with some of these things that you might get asked to do, one of these parts might be, so in this case, my two parts are going to be t or e to the something or other. Both of those are relatively easy to differentiate. All right. If I were to, but I'm going to have to differentiate one and integrate one. All right. If I integrate this one, I'm going to end up with a t squared, and that's going to make it more complicated. I don't want to do that. All right. So it's really important to sort of have a bit of a look. One of the other ones that gets asked is if I have an ln in there, I can't just integrate ln. ln requires an integration by parts itself. So I would organize that to be the part I differentiated. So there's a little bit of looking at what you've been given and what's the best way to do this. So in this case, I'm going to go, hey, my g is going to be equal to t, and my f dashed is equal to f dashed is going to be equal to e to the minus 0.05 t. And so when I go g dashed, that is going to be equal to 1. And when I go f, when I'm integrating this, so minus 1 on 0.05 times e to the minus 0.05 t. Notice I put the minus in the numerator. There are some little things that stop you, that help you avoid making mistakes. All right. Minus signs float to the top. All right. If I have a fraction, right, where the denominator is negative, that minus sign can float to the top. So put it together. So I've got 5 times the integral from 0 to 10 of t e to the minus 0.05 t with respect to t is equal to f times g. So minus t on 0.05 e to the minus 0.05 t minus integral. Now, this has got limits of integration, and what I'm actually going to do is I'm going to do a dodgy. It's kind of poorly explained how we get around doing this, but I'm just going to finish this. So notice the original thing was these two. I've done those two for this part, and now these two are the second part. So this is minus 1 on 0.05 e to the minus 0.05 t. And I'm going to evaluate all of those at 0 and 10. Okay? So get around expanding out what's going to happen there by sort of putting the limits outside. Minus t e to the minus 0.05 t on 0.05. That minus is going to come out the front, and so that's going to be plus 1 on 0.05 integral e to the minus 0.05 t. I'm going to evaluate at 0 and 10. And so this time we're going to do minus t e to the minus 0.05 t on 0.05 plus 1 on 0.05 minus 1 on 0.05 e to the minus 0.05 t, 0 and 10. And so this is going to get me minus 10 e to the minus 0.5 on 0.05 minus e. There's a thing where I had a 5 out the front here. I kind of forgot about that 5. We're going to put it back afterwards. It'll be fine. 5 on 0.05 squared. Then it's going to be minus, and then when I put in 0, that number is going to be 0. T is 0, that number is going to be 0. When I put in 0, this is going to be minus 1 on 0.05 squared. All right. Never have any idea what this thing is doing. Excel. Come on, sweet. Okay. We are going to give ourselves a cell, and we're going to go 5 times stuff. And then we're going to go minus 10 times by. So you had to do Mobius things. Mobius and Excel are friends. They use the same system for putting in functions. And that means when I want to do e to some power, I do exp and then the power. All right, that looks like a thing. Put in the appropriate thing. Going to divide that term by 0.05. That's going to be fine. And then I'm going to go minus exponential function minus 0.5. That thing divided by, and so making sure I get that right, and then that's going to be plus 1 divided by 0.05. Wait. Oh, I forgot something back up. I'm just going to go, that's equal to 180.408. All right, let's go back to this thing. Cannot emphasize enough how much I recommend just putting things into Excel or a calculator. Excel is nice because it's like a bit easier to edit, I find, but GeoGebra, Desmos, Symbolab, the list of computing packages that are available to do it online are ever growing. Do not use ChatGPT. ChatGPT is not intended to do mathematics. Do yourself a favor. Don't do it. There is, like, if you need maths done, there is a thing called Wolfram Alpha. Do maths on Wolfram Alpha, not on GeoGebra. Okay, let's see if we can't find something that's integration that is a different thing. So just before I move on, right? This formula, you can like, I write it out every time for myself. I write it out and then I use it the way I've written. Quite often, I only do it with F's and G's, and quite often what's here changes, but it's still the correct formula because I put it, if I put it on F here, I put it on G here, or vice versa. And so it's not, it is a difficult thing to use, but but it's important that if you are consistent, you will be right every time. Okay? Techniques of integration. We should do that. Let's find something fun to integrate. Not that. I reckon I'm going to do something a little bit out there. I could be wrong. This could be a great idea or it could be a terrible idea. All right. And if I do the integral of e to the 2x plus e to the x with respect to x, I'm actually going to do this in a different way. All right. There's an easy way to do this. All right. But it's not doing the thing I want to do. So I'm going to do this in a different way. Because I can write this as the integral of e to the x by e to the x plus 1 with respect to x. Okay? Followed me so far? So, substitution. Let u equal e to the x. All right? So, first thing I do once I decide my substitution is I differentiate. So, I'm going to do du on dx is equal to e to the x. And I'm going to write du is equal to e to the x dx. Now, see how I've got a e to the x dx? I can put that in. So I'm going to replace that bit. And so this is going to become u plus 1 du. So, for those people playing at home, one of the guys in the audience has got that. Why would you do that look on your face? And the answer is, I can do this, all right? It's not wrong to do this. I wanted to demonstrate substitution. And this is a substitution people don't often see, all right? Possibly there's a reason you don't see it very often because this is the hard work way of doing it. That would be u squared on 2 plus u plus c. But then I undo my substitution, all right? So this is going to be e to the x squared on 2 plus e to the x plus c. This thing here, e to the x squared, if we remember our power rules, this is just e to the 2x on 2 plus e to the x plus c. Okay, so I've got to the answer I knew I was going to get to, but I can express it as a substitution. Suppose the other one that we might be, I forgot to do that. All right, let's try something a little bit more complicated. So I'm going to put 2x plus 1 here. And I'm going to go x squared plus x plus 5 cubed with respect to x. So I've deliberately made something that is more difficult. All right. This is where I don't actually have a choice. All right. The answer is almost always with this sort of thing, u has got to be the thing in that thing in brackets in the denominator. All right. So I'm just, sorry, I've decided what I'm going to make u. First thing I do is I differentiate u with respect to x. And I'm just going to get me 2x plus 1. Woo! And so du is equal to 2x plus 1 dx. And so you can see what this is going to work out to really nicely is this 2x plus 1 dx is going to become du. And that denominator is just u cubed. Maybe I could write this as u to the minus 3 with respect to u. So when I integrate, add 1 to the power, u to the minus 2, divide by the new power. Remember to go plus c. I wouldn't leave it like that, all right? I would put the minus on the top line. I would go put my 2 here and go u squared and a plus c, and then I would undo it. All right, the reason I'm actually going to put it without a negative power, so there's two main reasons to not do things with negative powers. One of them is the more things with negative signs, the more negative signs you've got to stuff up. All right, bit of a thing. The other thing is this question was asked as a rational function. And so I want to write my answer as a rational function. And this is going to do this nicely for me. So I'm just going to be able to go, okay, minus 1 on, and then x squared plus x plus 5 squared plus c. It's an indefinite integral. I should remember the plus c. You will lose a mark if you do not put a plus c on on an indefinite integral. Okay, they will do that because they can. They have told you they're going to. They will go, and they will politely go. They will take that mark. Which, while I do characterize the person marking your exam as having joy at taking marks off you, actually, like I said, I've done a lot of marking exams in my life. I do not like taking marks off you, but I have to have a reason to give you marks. Okay, so I need to see something. And so my key point earlier was you need to write stuff down. Other techniques. So substitution is the best one. Do we have questions?
It's two times m squared, right? So when
yes, thank you. This is what I mean by I do stupid things all the time. I've been pretty good, usually caught them as I'm writing them, but yes. So that is that's a good question. Yesterday it was like, why is there a minus 1 in there? I'm like, oh, because it's part of. I'm like, no, there was no minus 1 in that. I had accidentally written the wrong expression for the thing I was talking about because there was no minus 1. Today, little mistake. So, thank you. So do we there's the list of functions you've got are relatively small. All right, the list of things you have to, well, you don't have to do a lot of integration with trig formula. All right, and trig substitutions. Did you do trig substitutions? Good. I didn't check before I came here today, so I was like, but you haven't in the past, and I didn't want to go there to this time if I don't have to. So almost always you can do a substitution. All right, you can try and do a substitution and admit that you've got it wrong. That was not the right thing to do for this problem. There is nothing wrong with starting a problem and going, hey, like literally the last exam I did, which is a while ago now, there was this horrible technique and I could never remember. Well, you had to create a model. And the creating of that model required making an observation about your system that I never quite got the hang of doing. And I knew if I tried enough, if I just threw enough models at it, I'd get it. So I redid that question like 10 times. And I got most of the marks for that question. In fact, the marks I lost for that question constitute half the marks I lost for that exam. But it wasn't until I was walking to the car on the way out of the exam that I actually remembered what it was. I actually worked out what it was. I'm like, so close, so close. If you can make mistakes, you can demonstrate the process, demonstrate that you understand how to do this. The key part is you get no marks for writing nothing. If you write something, you actually give me a chance to give you marks. All right. And I don't know, who's the coordinator for AQMF this year? Adrian Kerber? Yep. Adrian basically in the same boat as me, right? We want to give you marks, but you have to give us a reason to give you marks. All right. So I know he will be fair about it. So it's about giving him the chance because he would rather make sure you pass. All right. Did we have any more questions? I feel like we're at 11 o'clock and I might just pull the pin on this now because that's a fairly long session. Thank you guys for turning up and for your attention. Thanks for everyone online. This will go online soon enough. And good luck with your exams.